Thanks a lot, Stefano. It's wonderful that you mentioned this really tough spots. Put the bar possibly out of you. Not even try to be funny. I'll sort of chime a little bit on the theme of exploration in this talk. In particular, we can use some particular guides, exploration, both efficiently and safety. Something that wasn't discussed as much in the previous talk, so we'll talk a little bit about that. Of course, the work I previously studied on PhDs producing postdocs and Sleepolabicus, so a lot of knowledge as we go along. This talk is really going to be on the dry side of that spectrum. I'll try to make it not too dry, but here we go. So it's sort of silly to explain RL as RL doing. So obviously, this abstract model of an agent that tries to change the world through its actions, to get some reward. And we all know that one of the key challenges is that the agent doesn't know how to do it. Right? So the agent needs to experiment with actions to learn about their consequences, and it needs to use what it learned in order to do that. Right? And this is, of course, the key core problem of RL. Now, RL has been around for decades. Some of the key luminaries are in this room here. But at the heart of the many breakthroughs in AI, in data, robotics, colleagues in TH use RL to have robots to hike in the Alps, for example. I'm not sure why they would want to do that, but it's wonderful. So our colleagues at the University of Zurich use RL to have drones flying faster than pilots. Obviously, RL is not used extensively, so language models sort of go beyond the tasks that they try to communicate, and so on. That said, even though RL is sort of motivated as this paradigm of agent learning by interacting with the real world, that's not really how it's done. Right? So the settings where RL has been successful are basically settings of the computational model. Games of an example of this, precising how the world looks once we and our want to move. A lot of robotic settings, you can really build high precision physical simulators for locomotion and so on. And in those settings, exploration is primarily a computational one. Right? And modern policy techniques are really a powerful hammer to solve these problems at very high. Now, there are a lot of applications you might want to think about using RL, like precision agriculture, maybe medical applications, scientific discovery, and maybe having robots go and learn in open-ended tasks. I think it's going to be very hard to build realistic enough speed. So if there's lots of progress there, if you think about science, physics of science, figure out how the world works. Okay? And so now the question is kind of how do we address these sort of challenges? Today, and now, of course, exploration is now no longer a computational concern. It means trying actions without no consequence, potentially expensive, and of course, potentially safety. And so it's really a core challenge how do we enable these agents to learn reliably online, to interact with the real world efficiently, but also safely. And in this talk, I want to talk about some of the work that the group has been exploring in this space of safety efficient. And I'll start with the model of safety optimization. That's motivated much of the work we're going to talk about. And so here's a motivated application. So this picture here shows the Swiss Tree Antigen laser. That's a large scientific infrastructure in Switzerland, a 700-meter-long linear accelerator operated by the Krause Institute that generates X-ray pulses of extremely short duration, 10 to a second duration, 1 millionth of a billionth of a second. So you can use this to image extremely fast processing. Molecules transforming other complex chemical reactions, hugely important for materials discovery, drug design, and drugs. It's also a very complicated machine, with many literally moving parts like magnets that need to be repositioned that affect the beam in various different ways. The beam also depends something on the environmental conditions like temperature, humidity, and so on. It needs to continuously be adapted to application. So you can't just set this once. You can simulate the physics behind it, but simulation is incredibly slow. It's very hard to really capture the amount. So it means you really need to do this as the machine is in operation. You also don't want to break this as well, so it's pretty expensive. Okay, and so if you're not careful, then the beam can sort of demagnetize the magnets, and that's what we allow you to do over time. So now if you go about this, you can sort of think about as a very coarse abstraction. This laser is just a big black box. that you can inject some parameters through some tuning parameters. And then sort of observe something about the beam, right? And use a reward function, intensity, or how close we are to the target requirements. But fortunately, there's also lots of sensors that allows to monitor how close we are to violate in some. But the trouble is neither the reward nor the constraints are on that. That means we have to learn them as we go, right? And based on data we've collected, we want to kind of align that. And of course, again, we kind of want to maximize our rewards, but not just find a feasible solution at the end, but every single step along. So basically, you have this really difficult, non-convex global optimization problem with stochastic zero-order feedback, while having to guarantee feasibility every step along. So you should be pretty clear to everyone that this in general completely unfolds problem. So without any assumptions, you're not going to get any. And of course, now, the natural way to impose assumptions is to take a Bayesian viewpoint. That's exactly the idea, taking a Bayesian optimization, and we sort of try to model this black box with kind of a probabilistic history. So the idea is sort of as follows, right? That's kind of how Bayesian optimization generally works. So suppose we've taken a bunch of measurements shown by these pluses here. Is it fun here? Okay, like here, these pluses basically a bunch of data points. Okay, and I'm just looking at our posterior distribution modeling basically is a posterior mean by this black box and the uncertainty about it by this distribution. And now this model is well calibrated in the sense that it captures kind of the true underlying objective. You can sort of apply a smaller market. So let's take a pessimistic estimate of what look at this green dashed line here. Then, if the model is well calibrated, the optimal value must be somewhere above it. Right? So within this green subset of the domain, the sort of plausibly optimal. And this kind of idea and reasoning is the heart of a lot of algorithms and exploration and rapid state of decision and the likes. And for example, it motivates the optimism in the case of uncertainty principle, and of course, it's also core to exploration in RL, just as an acquisition function, you pick the point that sort of maximizes. But one can apply a similar reasoning for a state, right? So you could build confidence not just for rewards, but also for constraints. And then kind of, instead of being too optimistic, it's problematic if you want to be kind of too optimistic and things can go wrong, right? You try to be pessimistic about the constraints and you restrict your exploration to kind of a subset of the domain that you can sort of statistically certify these. Still sort of to the slides. So a pretty natural idea, you might do this first, is to say, well, let's always restrict ourselves to this data set, but otherwise it's a standard algorithm for exploration, like optimism and fixed points. Right? The problem with this is that you very quickly get in a situation where kind of these plausible optimal actions are contained in the strict interior of what you can certify. Okay? That means in order to make progress, you need some sort of incentives to explore beyond, right, just kind of plausible optimal. So one way to do this is to explicitly reason about expansion, a certain set of points that basically allow you to plausibly infer that additional actions to sort of push the boundary of this statistics. And if you do this, then basically you suddenly discover that there's much better region of the right, and eventually, and some regularity conditions crudely converge to sort of the regional notion of optimal, while guaranteeing safety. And so that algorithm and variants of that, we're actually running on this machine. So this picture in the top right here shows former PhD students of mine, where you're looking at this Krishna, Applied to the Bolshevik Institute, running this algorithm and operating room of this machine, where it does pretty well outperforming the heuristic that it is there components in this context. And there's been lots of other applications around state spatial optimization in the context of robotics, applications, including controller parameters, building automation, medical rehabilitation, and the others. But what I want to do in the rest of this talk is to address some of the key limitations of state spatial optimization and sort of bring it closer to general runtime. And so one of the key issues with state spatial optimization is that generally it really only works in relatively simple, relatively low dimensional movements. Right? So this example I described before, that's sort of 24 genetic parameters that need to be on. Still kind of relatively simple. If you think about learning complex behaviors, robotics, right? By using a network policies with millions of parameters, right? No way in optimization parameters. So we're going to talk about how to sort of take some of those ideas and make them work in the context of reinforcement learning. And sort of the key objective here is to sort of not reinvent the wheel, and to make use of this powerful hammer, the policy grading algorithms, like the grading algorithms that we want to use. So to do that, we're going to take a model-based perspective. So we're going to build a probabilistic model, but in this case, over the unknown dynamics. Okay, so this cartoon picture in the top right, in sort of the one-dimensional cartoon, just shows the plausible next states you might reach if you play action AT in state 2. And then what we can do is we can sort of forecast consequences of rolling out to the policy. So if you want to reach from state 1 S1 as a goal state, you might sort of contemplate different policies to consider the actions you want to carry out, and sort of think about plausible consequences of following it. And of course, the world will probably not quite work as kind of we had optimistic hope. But hopefully we're going to learn something useful along the way. And certainly it's going to contract, shrink, and we can act less conservative. Right? That's kind of the key idea in general, sort of structure. And you can apply similar ideas not just to guide exploration, but also to think about constraint satisfaction. And so if there are now this sort of a subset of states that are undesirable, right, that we don't want to get to, then you can try to only constrict yourself to use policies that don't visit it. That's sort of the cartoon, and all the question is how to make these ideas work. So we're going to go to basically going to take a Bayesian perspective on our models. We're going to quantify the epistemic uncertainty of what we know, what we don't know about the unknown objective. And we'll proceed in sort of the episodic fashion. In every round, we first start with sort of the prior of the dynamics model. We might start with some initial data, maybe it's empty, maybe we already have collected some behavioral data. And in every episode, what we're going to do is so take the data so far, refine all this area, we get sort of these confidence estimates, this one-dimensional cartoon here. And now, based on kind of how this theory will lead about the dynamics model, about how the world works, we'll update our behavioral policy. Now we're going to roll out that policy to collect additional data and do it. And only the last step is really the interaction to put it up, right? That's what counts. So we're going to be really careful with actions that don't have specific numbers. Now, the key step is the second one, right? That's that we want to make sure we're able to use the standard reinforcement learning hammer to be able to solve child problems. So let's zoom into that step and look a little bit further about what's going on here. And so now, again, of course, what's the general goal in RL? What we want to do is we kind of want to optimize for a policy that maximizes return under the true environment, right? Under the true model F star, the true dynamics F star. Trouble is that we don't know F star. Okay? So, sort of the natural idea is, of course, to sort of try to learn the simulation, right? That's the general principle to pursue the model F star. So you're going to collect a bunch of data, try to kind of estimate or learn the dynamics model, and then use it in order to kind of estimate the words might be able to obtain along the way. Right, so that, of course, then allows you to use general principle RL algorithms on kind of this learned simulation, this learned dynamics. The key issue with this is that, of course, there's going to be model mismatch, model errors. And if you optimize a policy with respect to that estimated model, the optimizer is going to be very good at exploiting model errors. That's the general failure mode of models. And moreover, of course, here you can only do so well as the simulated model that we basically have learned from data. Right? There's no explicit incentives to learn more and sort of get a better model of how we want. Now, one approach that's been very successfully used in the community to address this challenge of these model errors is to use the uncertainty inside of this model and say optimize an expectation over the uncertainty inside. Sort of hedge your bets against different dynamics models that are supported by them. That's the plus. That's the hard one, for example, the build method, the production process dynamics, or using vision events in Hess algorithm. And so the advantage is that this is much more robust in small errors. You can't exploit errors in single dynamics model we estimated. And you can still use those standard parallel, still just as stochastic optimization. Now, the issue is that there's still no explicit incentive to explore, and you can get stuck in this optimal solution. Now, the question is, how do we implement ideas like optimism? How can we think about optimistically exploring in this setting? And so the general idea of how to implement optimism models around is to consider sort of a set of plausible models, right? And then maybe that are plausible given all the data we've collected up to this sort of. And then try to optimize basically an optimistic estimate of the value that we could obtain so far. The key issue is that while that optimization problem can be exactly solved in, say, tabular setting, right, or in simple environments, if we have complex dynamics models, say with the Orlando functional approximation, this is a very complicated non-convex. It's very hard to. And so that is where a simple trick will also help make real progress. And so turns out what we can do, instead of solving this very complicated sort of constraint and optimization problem, all we need to do is to just modify the reward. Okay? So what we can do is to basically not just optimize the standard extras to the reward R, but just add a little bit of kind of sort of exploration bonus that basically takes into account the epistemic uncertainty in the dynamics. Okay, so basically we'll add this exploration bonus sigma n of st here, which basically just measures the amount of uncertainty that we have at this given state or state action pair. And so what we can show is that this builds through the optimistic estimates of the corresponding value function. It's just now a standard approximate programming problem. You can throw standard policy gradient algorithms at it. It's just a slightly modified reward function, so just extrapolate plus intrinsic reward. And again, under some regularity assumptions, we actually guarantee some linear regrets of that resulting out. So it's probably not going to be some solutions, assuming we can sort of solve that in optimization. Okay, and so now, of course, sort of intrinsic exploration is really a key notion. There's various exploration bonuses that have to be explored in the community, and this makes a very natural link, I think, between exploration bonuses and optimistic exploration bonuses. And so what's nice about this approach is you can basically just plug and play with any model-based RL algorithm you might want to use. And BPO, for example, or the Dreamer algorithm, the only difference is basically change the reward term, right, at this epistemic uncertainty term. And especially in difficult environments where you really need to systematically explore like sparse environments and certain types of target games, right? To talk about the target games before, this can really make a difference between solve the problem. So now coming back to safety, right? So this is about kind of optimistic exploration. So how can we think about sort of safe exploration in this one? Now, one way to think about safety in RL that has been considered quite a bit is to not just have a reward, but also having constraints that basically constrains the behavior of the agent. And so what we can, for example, do is to just have a task function that indicates whether the agent misses from safe states, in which case it's constrained, it's basically agent, right? Constraining the probability of disappearance. You might use other task functions and barrier functions so that they encourage these agents to stay away from safe states. And I'll say standard constraint to solve this, so basically try to solve this constraint problem under the true dynamics of stuff, right? Assuming example-based access to the end. But the key challenge we really want to address here is that we don't have perfect computational model, right? Where the stars are not known. And so kind of a natural idea is to say, well, let's consider a set of plausible dynamics, that was before, and use sort of an optimistic estimate for our reward and a pessimistic estimate for the constraint. Right? That's kind of a natural first step here. And now again, like you have this difficult complex constraint, but using the techniques that I've described, one can just turn this into standard CNDP formulation that one can actually practically see. And so that kind of further explains the state optimization, right? A remark that if you just kind of optimize an optimistic estimate of the reward under a pessimistic approximation of the safe set, you might get stuck in poor solutions. You have to think about expansion, right, to provide an incentive to kind of push the boundary of policies that you can consider safe. You can very naturally do this case as well, just inflating the intrinsic reward team. And that basically allows to really expand this safe set that we reach. We get some regularity assumptions, one can guarantee conversions to a natural motion. Here's just a cartoon illustration on the inverted pendulum problem. This has a two-dimensional state space. The angle, the x-axis, the y-axis is the angular velocity. You want to reach this topmost state here. If you just do active exploration, but unconstrained, you very quickly kind of search the state space. But of course, we might need constraints, and we can incorporate these constraints to still very quickly kind of search the relevant part of the state space and find an optimal policy without actually finding it. And these ideas also scale to standard benchmarks that have been considered in the safe harbor literature, like the safe region benchmark. There it goes to control simple robot models, like a simple car model or a quadruped, with a bunch of different tasks, like reaching a goal, touching buttons, or moving a box to a particular goal, all from sort of cognitive-based pixels, and the algorithms to scale to these types of problems. Here's a comparison with model-free methods that CPO, it's a constrained variant of PPO, that is very effective with CNDP solver in general, in terms of computational efficiency, in terms of the number of interactions required by the environment. It requires a lot of interactions. That's what the model-based provide. That's the advantage is model-based solver for CNDPs that much more quickly finds high rewards and feasible solutions, and using these area optimizers can actually ensure that this is even during that. So here's a true illustration of the simple robotics problem. What we want to do is we'll basically take this RC car and reverse park it on this designated parking spot over here. It's not a particularly complicated control problem. But if you want to simulate it precisely, you have to worry about materials properties, slippage, maybe aerodynamics effects, and so on. Really just building a precise enough simulator for this task not to fit. And if you use kind of a simpler model, bicycle model, so and do system identification on it, and learn the simulator, then you quickly get sort of sim to real gap, right? And it's just a policy things learned, simulate your one. And so instead, if you really learn essentially a policy from scratch, so this is basically starting knowing nothing about physics. The prior just makes some basic regularity assumptions. Then the first couple of episodes find us still violently out of control. But after about 50 episodes, so it sort of goes in the right direction. About 20 episodes later, it finds useful policy. Right? So basically relatively small number of episodes. Now, of course, for a problem like this, there's a lot of prior knowledge, right? That you would probably want to use. And that's where, of course, the creation paradigm offers very nice opportunities to kind of incorporate prior knowledge into the shape of this prior to kind of make data much more, make learning much more data efficient. And so one way to do this is to basically use the simulator and simulate a whole range of different dynamics. I mean, very mass constants, very different parameters, and technique that's extensively used with domain randomization and training policy to robotics. And that kind of offers a whole range of kind of plausible dynamics for PhD types. And so what we are going to do is basically sort of trying to learn a prior that compresses sort of the statistical signature of the simulator into a prior that we can then use for downstream. So I'm not going to go into too much detail of how that precisely works. So the key challenge is to sort of capture the statistical signature of this prior, to capture the interactions or correlations of the marginals of the stochastic process. So basically simulate kind of different solutions from the simulator and basically try to match marginals, not just at one point, but at arbitrary sets of points. And what we can do is we can basically just train a large neural network model that would give a set of test points, where kind of you would ask the prior of how it thinks the agent would behave, and then basically train it to predict the score. That's also that's needed in order to kind of learn and adapt the model from data. And so here's basically running the same algorithm now with this physics prior. And basically, even after the first episode, it sort of roughly gets the job done, but sort of the ramification. After about 5 episodes, it learns how to kind of turn around. About after 10 episodes, basically solves the task. And this is all kind of why it's entirely out of control during the right? So that's kind of a natural benefit one you get from this perspective, be able to really kind of do prior knowledge one has to do. It's very natural to sort of code that through simulation, so build this into the learning process. Here's some quantitative results of this. So this is really based on whole lot of data. So there's kind of prior data collected by driving around the car. This is a whole lot of data set which is trying to predict the performance. One baseline is just surface identification. So very simplified the model that of course strictly identifies the parameters that it is stuck. If you start with an uninformed prior, it takes quite a while to outperform sort of a simple model, but then you do better eventually as you have more and more data. A natural baseline is also grade-off small ones, also often considered. You sort of try to estimate the model and then just learn the deviations from that model, kind of learn that the estimated dynamics model is sort of incorrect, and they need to correct it in a little bit of fashion. And that helps to accelerate learning a little bit. But you can still do a lot better by basically readiness to directly towards some of these statistical bounds on all of and here's basically just the quantitative version of the video that I had shown you. Right, so basically you learn it more quickly and more really this knowledge. So that's basically what I wanted to talk about. So I think if you want to get closer to enabling real online RL, right, to enable agents to reliably learn online. If you don't know how the world works, every action you take is explored to the initial, whether we intentionally or not intentionally explore. It means you really have to think about efficiency and safety of exploration. I think that's really kind of the key challenge you need to address to realize the full potential of RL across scientific engineering. And I think one key challenge is to capture uncertainty, right? And to really be able to quantify epistemic uncertainty in very complex environments. So there's lots of progress now with foundation models, visual models, and so on, and they work amazingly well across very complex data sets. Uncertainty quantification, right, was really still very much a problem that these models struggle to success. And there are a lot of basic research. So with that, I'd like to conclude. Thank all the collaborators who's worked on your segment here, and of course all of you for attention. Thank you very much.
Thank you very much, Andreas, for the talk. We have some time for questions, and we have the helpers, I think, again somewhere.